Hi, my name is Dennis Angel. I am an XRPL core developer for XRPL Labs, and today we're going to be discussing transactors in the RippleD source code. For today's agenda, we're going to have an introduction to transactors, go over the architecture overview, the transaction lifecycle, validation concepts, the application of the transactions, some fee and sequence management, signature and permission checks, and then talk about some extensibility and I'll wrap up with a summary. So introduction to transactors. So what is a transactor? A transactor is a conceptual framework designed to manage the life cycle of transactions within distributed systems. Its primary role is to ensure that every transaction is processed consistent, secure, and in an extensible manner. The transactor framework abstracts common steps and checks required for all transaction processing while allowing both standardization and flexibility across different transaction types. So the first subject is the architecture overview. At its core, the transactor framework is built around the idea of a separation of concerns. It divides the transaction processing into distinct phases, and each are responsible for a different aspect of the validation of the application. So this modular approach allows for easier maintenance, testing, and extension of transaction logic. The architecture typically includes context management. So each transaction is processed within context that encapsulates all relevant information, such as the current state of the ledger, transaction details, and environment parameters. The base transactor, a foundational component that defines a general structure and flow for processing transactions, and then specialized transactors, which are extensions of the base transactor that implement specific logic or particular transaction types. So now we'll discuss the transaction lifecycle. It starts with what's called pre-flight. This initial phase involves basic validation of the transaction structure and intent. So was the transaction formulated correctly? Were the amounts correct? Are the amounts greater than zero? The purpose is to ensure the transaction is well formed and meets the basic criteria. Some examples are checking the required fields, correct data types, and validated values. The second is pre-claim. In this phase, the system performs contextual validation to determine if the transaction is likely to succeed given the current ledger state. In this stage, we have access to read-only ledger state. The purpose of this is to prevent transactions that are doomed to fail from proceeding further. Some examples are verifying that the account exists or has sufficient resources or that prerequisites are met. The final step in the transaction process is the application of the transaction. So if the transaction passes previous check, it moves to the application phase, or what we call do apply, where its effects are actually applied to the system state. The purpose of this is to execute the transaction's intent changes, such as transferring value or updating records. Some examples of this are adjusting balances or modifying data or triggering other events. The next section is validation. So validation is a multi-layered process designed to ensure that only legitimate and authorized transactions are processed. The main concepts include structural validation, so validation against the transaction, contextual validation, checks that the transaction makes sense in the current ledger system, and permission validation, which confirms that the initiator has the right to execute that transaction. The next section is fee and sequence management. To maintain fairness and prevent abuse, the transaction framework incorporates mechanisms for managing transaction fees and sequence. The fee management, so the purpose here is to deter spam and compensate for resource usage. The concept is that each transaction must include a fee, which is checked against system requirements. Insufficient fees result in rejection. And then the second part of that is sequence management, which prevent replay attacks and ensure proper transaction ordering, so that each transaction includes a sequence indicator which must match the expected value of the account or entity so that out of order or duplicate transactions are rejected. The next section is signature and permission checks. So security is paramount to transaction processing. The transaction framework must enforce this through signature verification. This ensures that the transaction was authorized by the rightful party. This may involve a single or multiple signatures depending on the required level of security. And then permission checks, which validates that the signer has the necessary rights to perform the requested action based on the system rules and account settings. And then finally, we have the extensibility of the transaction types. So one of the strengths that the transaction framework is its extensibility. The base transactor defines a general flow of these common checks, pre-flight, pre-claim, while specialized transactions can implement the unique logic specific to that transaction type. And the purpose of this is to allow the system to support a wide variety of transaction types without duplicating common logic. The concept here is that new transaction types can be added by extending the base transactor and implementing only unique aspects of that specific transaction's behavior. In summary, the transactor framework provides a robust, modular, and extensible approach to transaction processing. By clearly separating validation, application, and security concerns, it ensures that transactions are processed safely, efficiently, and fairly. Its design allows for easy adoption of new transaction types and evolving system requirements, making it a foundational concept of distributed systems. Thank you.